The Cambrian explosion gives us a lot of information about how organisms would have dealt with their environment, because we can start thinking about not only the fossils that are deposited after such a large explosion of life, but also thinking about the nutrients and elements that we can extract from the rocks that surround these fossils. So some of the earliest rocks that we have been able to date and find some signature of nutrients and elements that might be important for the development of life are actually some of the Precambrian rocks on the island of Greenland, and they date about 3.8 billion years ago. So when we talk about the Precambrian, the biggest thing that we need to think about is the development of high levels of photosynthesis, and really what we're interested in is that we need to build up oxygen, and photosynthesis would allow us to eventually do that. So when we look at the conversion of these organic molecules into something that we could better understand with current life on the planet, oxygen and photosynthesis is really our focus. So we think there were probably high numbers of cyanobacteria. These, of course, would have all been aquatic at this point, remember, because we're still dealing with very high UV on the Earth's surface. But think about the number of cyanobacteria and how this would have taken to build up. Very, very, very long time. We're actually looking at essentially no O2 or very little oxygen before about 2.5 roughly million years ago. But with this development of enough oxygen as a byproduct of photosynthesis to start thinking about how organisms could develop and adapt and select for traits that would allow those particular properties associated with higher order development, oxygen really is our key. Now, with an increase in the amount of oxygen that's around the atmosphere and available, we do start to see a die-off of the anaerobic organisms. Remember, anaerobic being oxygen-hating, okay? But this also allows us to start developing some organisms with nuclei, higher-level organisms, and so on. Now, we've talked before about the endosymbiotic theory. So the endosymbiotic theory states that one prokaryotic organism or early eukaryotic cell would have ingested a prokaryote or bacteria, and that in that ingestion actually didn't consume it or eat it like we would normally think, but instead it survived. And now what we look at is actually a mitochondria being very, very similar in structure and process to that original bacteria cell that would have been ingested. Why do we think this? Well, remember, bacteria and mitochondria both have their own chromosomes, okay? So they have singular circle chromosomes. And when we look at the development of these very simple early organelles inside eukaryotic cells, this one is especially interesting because it would have generated its own energy or ATP. So this really is the focus, that this early organelle was actually generating its own ATP. So what benefit does that have to the eukaryotic cell rather than just consuming it? You have to keep in mind that that eukaryotic cell now has a higher ATP level associated with it. It's going to use that ATP. It's better adapt to its environment. It can reproduce more, and the whole thing kind of snowballs from there. So with this buildup of oxygen, remember, O2 plus UV actually gives you ozone, or O3, and the intriguing part of this is we actually use UV, or ultraviolet radiation, to create ozone, which is going to block the ultraviolet radiation. And as we see that decline in UV that's actually reaching the Earth's surface, things start to go kind of crazy for us. So we see our earliest heterotrophs during this time. So remember, heterotrophs are organisms that can eat other organisms. So this is early order predators. Okay, and you can see the diversity. We've got sponges up here at the top. There's a whole lot going on. Now, many of these organisms are not going to look familiar to you. This is a tube worm of type. We still see a lot of those, but some of them are going to look very unique to you, as well they should. These are complex organisms for their time, but in general we would think about them still being fairly simple for what we know. Anomalocaris is one of the earliest predators. Notice the jaws in the front, the forward-facing eyes, and they would have been on the order of some of the earliest predators, but also don't have nightmares here. These things are not 6 feet long, but some of them they believe may have been up to a foot long based on fossil records. So interesting. Higher order predators, we start to see a development of larger body structures.